Okay, good afternoon, good evening, everyone, and welcome to SETI Live. We are broadcasting from Mountain View, California. Richard, where are you tuning in from?
I'm in Brentwood.
Brentwood, California.
Yeah, about 60 miles from you.
Okay, welcome. Well, welcome to everyone. I see we've already got a lot of people telling us where you're from. That's brilliant. Keep those coming in the comments. And we're going to have a conversation about observing with the James Webb Space Telescope, JWST. And I'm sure everybody who's watching has been as amazed and thrilled as Richard and I have over the last few days, seeing these incredible images coming in. Richard, what's been the response from you and your colleagues?
It's fantastic.
Yeah.
I mean, it's unexpected. I mean, it's unprecedented. The quality of the images is just phenomenal. And as we were talking about earlier, Hubble is no slouch, and the Hubble data is phenomenal, and the JWST data is just that much better. Yeah. So it's really, really exciting week, and really excited for the future of JWST and what it's going to show us.
Yeah. Just a question about, Hubble obviously is still going, but it's a bit of a sort of a classic car now.
Yeah, it's hanging on.
It's hanging on. Is the image quality, because there's a lot of images that have been compared between Hubble and JWST, is it purely to do with the optics, or is it detector quality as well? Obviously, the technology has advanced since Hubble's last refurbishment.
Right. I think that is a large part of it. You think, the Hubble instruments are much older. The original suite of instruments, of course, was built, or at least designed in the 70s and then built in the 80s. And there were some improvements, as you mentioned, over the years. But JWST's instruments are a much more cutting edge, much more modern, and a lot more sensitive. So that's definitely part of the improvement in image quality, along with the factor of 6 increase in gathering area, collecting area, which is always important for telescopes.
Yeah, that's neat. So welcome everyone tuning in. If you do have any questions for Richard as we go along, we will attempt to answer as many of those as possible. And one thing I want to start with, of course, is you are going to be a JWST observer. You have time on the telescope. We're going to talk a little bit more about that and what you're actually going to be looking at. What telescopes do you normally use for your day job? What have you been observing recently?
Right. So I'm mostly a solar system, or exclusively solar system astronomer. I'm interested in icy bodies in the outer solar system, primarily icy moons at Jupiter. So the Galilean moons, the big ones, Europa, Ganymede, and Callisto. And then also smaller ones like the Uranian moons, Ariel, Titania, Umbriel, and Oberon, which we'll talk a little bit about in a bit. And I mostly observe in the near infrared using instruments like spectrograph on the NASA's Infrared Telescope facility, which is on Mauna Kea in Hawaii.
So the IFTF, another infrared telescope, not in space, on the top of a mountain, and that says something a little bit about why have we bothered sending this thing up into a high orbit, and that's something to do with atmospheric absorption, isn't it?
Yeah, and that's a huge part of what I was going for in the Cycle 1 proposals, the ones that I put in to observe solar system objects, the Uranian moons, and then Callisto, the Galilean moon, is because they have CO2 on their surfaces, but solid state CO2. But CO2 is tricky to observe from Earth's surface because it overlaps atmospheric CO2, which absorbs very strongly in the near infrared. And so it's really hard, unless you are able to get above the atmosphere, to characterize CO2 specifically. There's other things as well, but that was a primary link between Callisto and the Uranian moons, is going after the CO2.
Okay. So let's maybe have a look, because we're going to be talking about spectroscopy. Of course, all the beautiful images are images and not spectra. My background is a lot in spectroscopy as well, which isn't as beautiful, but the amount of information you can get out of a spectrum compared to a visual image, I would argue, is much greater. Could you say, we're going to have a look at one of the first releases of spectra from JWST in a second, but say a little bit about what is spectroscopy, and what does it give an astronomer?
Right. So in very basic terms, when you're doing spectroscopy, you're splitting light up into a variety of different wavelength bins. So instead of looking at all of light in one go, you split it up into little segments, and then you look at how the flux or how the brightness of an object for reflectance, which is what I mostly deal with, changes as a function of wavelength. And it's just a fancy way of saying that's how you get the squiggle going from left to right. As the wavelength increases, then you see changes in the flux, in the brightness, and that can tell you some really important things about what you're looking at, what it's made out of, what the surface is made out of. For my objects, because they're solid bodies, I don't observe atmospheres, and so you look for what's called absorption bands, which show up in the spectra, and that can tell you about what's there. And so you'll see diagnostic absorption features that are characteristic of things like water ice, or on WASP 96b are characteristic of water vapor.
Let's have a look. Let's bring this up. Jasmine, could you share some images here? And these are from the image release from JWST yesterday. Possibly a bit overwhelmed by the beautiful pictures we saw. Then let's see if we can share these on screen now. Okay, so we're going to come back to those. So let's just start with the observations. This is the observation that was made. Richard, can you go take us through this diagram?
Yeah, I'll do my best here. So we can't directly observe the planet WASP 96b. It's even though it's a big planet, it's over 1,000 light years away, as is its star that it orbits. And so it's very hard to see this planet next to a really bright star. For a bit of background, the star is a sun-like star. It's solar-like. It's similar temperature, similar size, similar mass to our sun. And the planet, though, is really big. It's about, I think, 1.2 times the size of Jupiter. So it's a big one, but it's half as massive as Jupiter. So in other words, it has a lot less mass, but it's bigger. And so what that means is it's really puffy. It has a big atmosphere that's really puffed out. And that's part of why it made it such a great target for JWST, because it has a big atmosphere. We can characterize what's in its atmosphere. It's easier to do because it's so large. And what this diagram is showing you, it's just cartoon diagram. The planet is supposed to be that black dot going in front of that star. The planet is nowhere near that big. This is just a characterization, just an illustration. And the lighter gray area around that black dot is supposed to represent its atmosphere. And so what happens is the planet, which has a 3.5-day orbit, so it's very close. So for reference, its orbit, I think, is 1/9 the size of Mercury's orbit. So it's really close.
Right in there, yeah.
Yeah, and it's hot. This is a hot star. So this planet is absolutely baked. And we'll get to that, because using the spectra, they've been able to estimate the temperature of the atmosphere. So we'll get to that. So anyway, so as it orbits around its planet, orbits around the star. It transits the star. And so what they're able to do is they look for a difference in flux in how much light's coming from the star when the planet's in front of it, and then when it's not in front of it, and they can compare the two to characterize the planet itself. And so what they do is they collected spectra using the near-infrared imaging slitless spectrograph on JWST. And they looked at starlight from that star coming through its atmosphere, through that gray area around the black dot. And then, like I said, they compare it to when the planet is off star. And then through that comparison, they're able to isolate the information coming from the planet's atmosphere. And that's what that spectrum is.
Okay, let's have a look at the spectrum. So you take a spectrum of basically the star and the planet, and then a spectrum of the star, and you subtract it, and what you got left.
I think so. Yeah, I think that's what they did. Right, and this is a transmission spectrum. So this is different than what I normally do. But this is what...
That's a good point. We'll come back to this. And so this is... let's have a look at the spectrum anyway. And here it is.
It's fantastic.
So what have we got on the axes here? Just break it down, what we're sort of appearing.
Right. So I think I can't quite read it, but the y-axis is drop-in flux, or how much the brightness is changing. And so as you go up the axis, the brightness is dropping more. And so that means that the planet is contributing more of the signature, the spectral signature. The x-axis is wavelength, and this is in units of microns. And I believe it starts at 0.6 microns. That's about the shortest wavelength that JWST is sensitive to with the instrument suite that it has. And for context, our eyes can see about 0.4 to 0.7 microns. So this overlaps a little bit of what we can see with our own eyes.
Just the
but
end.
Most
I think that's
of it.
something, yeah.
Sorry,
Sorry, that's something important is that
Yeah.
none of these images that we're looking at from JWST, it's all invisible. Our eyes cannot detect any of this stuff.
Right.
And it has to be, you know, the colorized. Astronomers call it false color for the image, but you know, you have to sort of change it and sort of translate it into human vision, don't you?
Right. Yes, you do. And so some important details that we can glean from the spectrum. So what are we looking at, right? So those peaks, which are labeled water vapor, those are characteristic absorption features in transmission. So where there is less light being transmitted through the atmosphere, remember, we're looking at starlight coming through the atmosphere to us, to JWST. And so where there's less light coming through, that's where the planet is doing more of the absorbing, or its atmosphere. And so this is where we see the water vapor. So they're peaks, water vapor peaks, and they've labeled 4 of them. And so that's pretty diagnostic. When you start to get to that number of spectral features, that's a really good sign. So that I think they really nailed it. The other thing I was reading about before we went on is that the peaks are actually smaller than they expected. And so that tells us that there's more scattering from clouds. So this clouds are actually, the scattering from the clouds themselves is reducing how much the water vapor is able to absorb. And so that's decreasing or increasing the transmission, I guess, decreasing the opacity. So that's interesting. So that's something that we can get from this. The other thing is, based on the heights of the peaks, they estimate that the atmosphere, I have it written down, temperature is 725 degrees Celsius. So this thing is hot. And that helps explain why it's so puffy, right? The atmosphere is so hot that the whole thing is expanding out, which helps explain why it's so much bigger than Jupiter. And then another little detail that I read about that's a little bit hard to see, but at shorter wavelengths, maybe between 0.6 and 1 micron, they say there's a little bit of a slope there where the flux kind of falls off a little bit to the left. And they think that might be characteristic of haze. And so along with getting composition, with the spectrum, we're actually able to get temperature and also some crude structure to the atmosphere in terms of clouds and haze layers. So really informative.
That's amazing. So if it's cloudy, then the light is just bouncing off, so it's not being absorbed by the atmosphere, but also how transparent the atmosphere is once you get through the cloud is what you're getting here. That's and all from these squiggly lines, as I said, spectra. Very, very useful indeed. Now this is a sort of a severe sauna planet here. We've got incredibly high temperatures. We've got the water vapor. Water is very common in the universe, and you know, we're not expecting that this is any way indicative of, you know, a potential for life. But being able to detect these signals for water is going to be quite interesting, isn't it, moving forward?
It is, and I don't know how unprecedented this data is. I know that I think beyond 1.6 microns, so between 1.6 and 2.8 in this plot, I don't know if that's been done before for this object. So that may be a first. It's certainly higher quality than anything that's been done previously. So it's really exciting.
Yeah, that's really, really good. We're going to kill the slides for a second because we're going to move back to our own solar system. Now this is a planet going around another star. It's 1,000 light years away. And of course, exoplanets, now we know of 5,000 exoplanets. Detecting the atmospheres of the larger planets are going to be easier for JWST than the smaller ones. But we're gonna return ourselves back home, if you like. And none of the images yet. There's been an image of Jupiter that's been released, but a lot of this is you know, cosmological large distance. But your interests, Richard, are slightly more sort of
That's right.
suburban, as far as I guess not really an insult.
Yeah,
Much
right. No, not at
closer,
all.
closer to home. And I think
Yeah.
it might be good just to have a look at the objects you're interested in, which have been the difference here is that these objects are in our own solar system. They've been visited by a robotic spacecraft, haven't they? By the
Right.
Cassini mission and by Voyager. So let's just take a quick peek at the types of objects you're interested in, and we can look at the features that we know about, and then see how JWST is going to enhance our understanding of these. So, Jasmine, just put these slides up again, and we'll have a look at. We'll start closer to home. This is the Galilean moon around Jupiter. This is Callisto. And say a little bit about what we're seeing here, Richard.
So this is an image mosaic put together, I think, with Voyager, either Voyager or Voyager 2 images. It might be the first Voyager. And this has also been imaged by Galileo back in the 90s and early 2000s, but hasn't been visited since by spacecraft. Juno is in the Jupiter system right now, but its focus is mostly, in terms of the moons, is Io and Europa and Ganymede. It's not visiting Callisto, unfortunately. So no spacecraft will visit Callisto until Clipper and Jwst get there. And then they both will make close passes, which will be really exciting. But in the meantime, telescopes are the main way that we can learn about Callisto. Now, originally, the idea was when we got these images of Callisto from Voyager that it was an ancient planet or an ancient moon. There wasn't much going on from a geologic perspective, and it wasn't interesting. Well, turns out that's not really the case when you consider spectroscopy, because Callisto has an absolute wealth of chemistry happening on its surface. Some of it's being spurred by interactions with Jupiter's magnetic field. Some of it is from infall of dust. Callisto is relatively warm, so a lot of volatile ices sublimate. So there's some migration of molecules across its surface in response to subsolar heating. And so Callisto actually is pretty active. It's just not in a traditional geologic way.
Yeah. No, it doesn't have an atmosphere. You say there's some sort of sublimation. There's some volatiles, due to the interaction with Jupiter's magnetic field and things like that, but no atmosphere.
Right. It doesn't have what we would consider an atmosphere, but it actually has more of an atmosphere than most icy moons. Obviously, the moon with the largest atmosphere is Titan, which has a huge atmosphere, bigger than Earth's. And then after that, there's a big drop off. And you've got Triton, which has a very thin atmosphere. And then Io, which has a volcanically spurred atmosphere, right? It's constantly erupting stuff into orbit. Then you've got Callisto, which actually has what's considered at least parts of its atmosphere are considered collisional, which is it just means that parts of its atmosphere, the molecules are actually close enough together that sometimes they bounce off each other, as opposed to something that's more tenuous and the molecules are much more spaced apart. So Callisto actually has a bit of an atmosphere for a moon. And we think it's rich in oxygen and in carbon dioxide. Now, we have some information from Galileo, from the Galileo spacecraft. But those data are useful and compelling, but the technology is pretty old now. And one of the things that we think about in spectroscopy is spectral resolution. So when I said that light gets split into these little bins as a function of wavelength, how many bins do you have? How much do you split that light? And Galileo, NIMS spectrograph on Galileo, didn't do very much splitting. And so it gave us a useful picture, but it didn't give us the full picture spectrally. And we filled some of the gaps in with ground-based observations. But as you mentioned, Earth's atmosphere blocks a lot of wavelengths because gases in Earth's atmosphere are absorbing. So you got to get above the atmosphere in order to see those sorts of species constituents on its surface, CO2 primarily. So one of the main things we want to do with JWST is characterize CO2 across its surface, figure out, did it originate in its interior? Is it a radiolytic product? Or in other words, is a mixture of carbon stuff and water ice that gets irradiated by Jupiter's magnetosphere? Is that how we're making that the CO2 gets made? So there's a lot of questions here on the origin of volatiles on its surface that we want to try and answer with JWST.
Okay. Thank you. We're going to say a little bit more about Callisto. I'm just going to call out some locations where people are tuning in from. We've got Glasgow in Scotland, Queens, New York, Fairview in Canada, Sao Paulo, Brazil. We have Maryland, Brooklyn, the Netherlands, Dallas, Poland, Vancouver, and as I scroll down, Salt Lake City, Scottish Highlands, and Wales and Mexico and Hamburg. And I will stop there, and we will come back to that list
Cool.
in a little bit. So the surface of Callisto, we saw it's a pockmarked, presumably recent impacts have produced the sort of white specks where the sort of pristine material.
Yeah, water ice mostly.
And you're going to get the light that's bouncing off Callisto, which is sunlight, of course.
Right.
That's how we illuminate it, or how it's illuminated, and you're going to break it up into the spectrum.
Right.
So say a little bit more. You're going to detect, presumably the ice is there, a carbon dioxide and water ice. But what specifically, apart from detecting CO2, what are you getting out of that?
Well, we're hoping to figure out what its origin is. As I was saying, is it is it from the interior? There's some landscape evolution models that suggest that the CO2 originates from its interior and has just been leaking out over time. Or is it generated on its surface from charged particles? But one of the things that we want to get at is that CO2, like a lot of other molecules, can be made with different isotopes. And so with CO2, you can have 12 CO2 and then 13 CO2, which is the slightly heavier but still stable isotope of carbon. And you can ratio the 13C to the 12C by measuring spectral features at different wavelengths that are characteristic of 12 CO2 and 13 CO2, neither of which you can see from the ground. You've got to get above the atmosphere to do it. And then you can compare that to other isotopic ratios throughout the solar system to see how the formation conditions compare at Callisto relative to Earth or main belt asteroids or to Mars, etc. And so that gives us a better picture of how the solar system formed and where different materials and chemicals were at the time that the moons formed and that Jupiter formed, etc. Okay.
So the slight difference, the extra mass for a carbon-13 nucleus is enough to change its spectral signature to split that line. How much of a shift is it in nanometers between the equivalent CO?
Well, nanometers.
I'm sorry.
No, I could do nanometers. It's 100 nanometer difference. So it's 4.27 microns versus about 4.37 microns. So definitely JWST with near spec has the spectral resolution to discern those two features.
Right. And so with that, you can get the carbon 13-12 ratio from the ice, and that will give you a clue as to the origin of an evolution of the carbon dioxide. Right,
and also it gives you a sense for what was the Jupiter subnebula like. Was it similar to the inner solar system? That's what I suspect we're going to find, but we won't know until we measure it.
Yeah. Let's have a look at the. Let's go out a little bit to the Uranian system, and we'll have a look at some of these moons. So here we go. Oops, go back a slide. So these are the four moons. Now these aren't to scale,
right?
But these generally are smaller than Callisto. These are
way smaller,
moons, aren't they? Yeah.
Yeah, and all of these images are from Voyager 2, and we haven't sent a spacecraft back there since then, and we might in the future, which I'm very excited about. But we're not here to talk about that today. Yeah. And the other thing is Voyager 2 did not have a near-infrared spectrometer on board. And so everything we know about the composition of these moons comes from telescopes, ground-based and space-based. And so it's really critical that we get good data from telescopes to help inform us, in terms of what they're made out of and where that material came from. And so similar to Callisto, we know these moons have CO2, but we have a similar sort of problem where some of the major CO2 spectral features are blocked by Earth's atmosphere. And so we're going to use JWST to go after those features, again, in the 4.27 and 4.37 micron range. So we hope to make the same sort of 13C to 12C isotopic ratio to see how the Uranian subnebula compares to the rest of the solar system. And this could be really exciting because Uranus forms, so some backstory, we think the giant planets migrated in the early solar system. And so Uranus and Neptune probably formed closer to the sun than their current semi-major axis, their current heliocentric distance. But they were still kind of far out. They're still on the edge. Yeah. And so their isotopic ratios could be really different because what we think happened, this is the general thinking, is that in the early solar system, the sun kind of, with ultraviolet light, baked a lot of the isotopic ratios in. And so it removed 13C preferentially in the inner solar system. And this is, we have some of these measurements for Saturn, and that holds for Saturn, which is why I expect that Jupiter will be Earth-like, because Saturn is Earth-like. Its moons are Earth-like in terms of the carbon ratio. But Uranus formed further out. And so maybe its carbon ratio is different because it was far enough away from the sun that it absorbed, the Uranian subnebula absorbed less ultraviolet light early on.
Okay.
So we're hoping to test that.
Yeah, yeah. So that'll give you an idea, not only the sort of, the locations of where these planets are forming.
Right. Also, yeah. Right. Also that. And the other thing that we're going to go after, the other thing that I'm really excited about is the spectral signature of ammonia. Now, ammonia is one of these very interesting molecules. When you mix it with liquid water, it helps reduce the freezing temperature. And so in essence, if you have liquid water in the interiors of these bodies and you mix in ammonia, you can keep it liquid for much longer. And this plays into the whole idea of ocean worlds. And so these moons might have been able to retain liquid water till the present. There's actually modeling results that are coming out soon, I hope, by another team that are going to demonstrate they may have residual oceans even today, at least the bigger ones. And so one thing we want to look for is the signature of ammonia. And from ground-based observations, we see hints of things in spectra that could be ammonia, but JWST should really help us nail it down.
So it's possible even this far out in the solar system. What are it with 30 times the distance from the sun, the Earth?
20 times. 19.2 AU, something like that.
Neptune is 30. I get my
right.
That there is a possibility that you could have liquid water oceans beneath the icy surfaces of these moons, which is quite amazing.
It is. Now, whether those oceans interact with the surface, whether there's conduits and you have, it's similar to Enceladus plume activity or something like that, that's a lot more speculative and exciting, but harder to support at the moment. But a residual ocean, just kind of sloshing around in the interior, it's starting to look like that's possible.
Yeah, that's would be amazing to find that out. But then you've got to go there, of course, haven't you? And that's another conversation.
That's another talk.
Well, a few more locations: Michigan, Richmond, Virginia, Kentucky, Minnesota, Alabama. So welcome, everyone. If you do have questions for Richard, please put them into the chat, and I will scrolling through the lists now, and we'll dig up some questions. When are you hoping to have your time on the Great Telescope, Richard? What's the plan?
Right.
As far as
right. So for Callisto, I've got what they call long-range plans, where they say, well, it might happen in this window, it might happen in this window. And for Callisto, it could happen later this month, or it could happen in August. If it doesn't happen then, I think the next window starts in December or perhaps early next year. So it should be reasonably soon. It could be really soon, or it could be about 6 months from now. Right. For the Uranian moons, that window, I think, opens up in August is the earliest those could happen, and that goes through October or so. And then the next window is into 2023 as well.
Right. So you could get some results this year. And how long, when the telescope, they point it, they get the data comes in.
Right.
What's the story of your electrons from that? How does it work?
Well, okay, so Callisto is interesting. It's really big. It's really close. it's really bright, it saturates really fast. So we are taking the shortest possible exposures that you can with Callisto in the highest resolution spectral mode, which comes with drawbacks, but we had to do this to try and avoid saturation. So if you split the light into more and more bins, you reduce the risk of saturation because you're just separating the light more and more. So you're weakening the signal in a way. So that's what we had to opt for. But there's drawbacks. So we, getting into the weeds there. But once we get the data, we will put it in our pipeline, or Space Telescope Science Institute have their pipeline, and they'll remove common artifacts, things that they know can happen, correct for defects in the detector, all sorts of stuff like that. Then they package the data and they send it to you. Then at that point, I'll have an image that will show the disk of Callisto, because Callisto will be spatially resolved. So in other words, I'll have a disk with lots of pixels over it, and each one of those pixels that covers a different terrain will be a spectrum, where you'll get that whole wavelength range. And so I can characterize the composition in each pixel across its disk. And so I can look for geologic differences because of the big Asgard and Valhalla impact basins, which are these huge craters that we're going to observe. And then there's another region of Callisto. So we're observing Callisto three different times. And then there's going to be another observation of its trailing side, where on the opposite side of Valhalla and Asgard, and we're going to compare them.
Right.
But the pipeline it doesn't exist yet. It's being built, and it's on the way.
Excellent.
Yeah.
Okay, let's have some questions here. So this is a question from Preedy, and this I think is going back to the spectrum of the Wolf star. Is the planet shedding its atmosphere, and can you tell if it has a magnetic field based on this result?
Those are good questions. I don't think we can tell if it's shedding its atmosphere, but I would be absolutely shocked if it's not. It's so hot, it has to be losing gas to space. It absolutely has to be.
Yeah.
So it definitely is losing it. Whether it has a magnetosphere or not, that's not something I've read about. So I would be speculating. Because it's similar in size to Jupiter, I would speculate that it does have a magnetosphere, although it's also a lot less massive than Jupiter. So I don't know what kind of core it has in order to have that convective layer that can generate a dynamo and then lead to a magnetosphere. I would guess that it does, but I'm really speculating about that.
Yeah. It's difficult. There's so much more to learn about the planet, isn't it? And we're just starting on that. Now, there's let's see. Richie says can you see planets in a Goldilocks zone? Now, we might need to say what a Goldilocks zone is for the audience, and this goes back to water, doesn't it?
Right. And so I think the general gist is, and I don't do exoplanet science, but I think the gist is it's a distance from the star for a planet zone, so a zone in terms of orbital distance, where you can have liquid water be stable at the surface. And so that we think could be a good place for life. And so you don't want to be too close to a star, but you also don't want to be too far that you freeze. You don't want to be too hot or too cold. And the type of star that you're orbiting determines where that Goldilocks zone is. So a lot of M-class stars, M-type stars, which are much cooler, you want to be closer.
Yeah.
Whereas with the bigger stars, you'd want to be further away.
And what the observations, obviously the release, this is the first spectral release for JWST, and it was chosen, as you say, because it's a nice target. It ticks all the boxes as far as JWST's capacity and capabilities are concerned.
Right. And I strongly suspect it is not in the Goldilocks zone, since it seems to be an oven.
Yes.
But right. So to that question, I think they're going to target those sorts of planets, but I'm not 100% sure. But I would be shocked if they're not.
Yeah. A question from Preedy, and this is about planetary migration, I think. And the question is, do you think it might later migrate to the outer solar system? I'm not sure. There's a couple of things here. One is the migration of this hot Jupiter in the WASP system. What sort of migration is that going to do? And the other one is just talking about migrations of planets in our solar system. Is this does this still happen, or is this something during the early phases of a planetary system?
It's not happening now. It's an early process where the giant planets formed. The whole solar system was much more condensed, we think, and then in the very early solar system, the giant planets migrated outwards. I think at least 3 of them migrated outwards, and maybe Jupiter slightly migrated inwards. It depends on what model you look at. But that's the gist, is after they formed, they started to move away from the sun, and this created a lot of chaos. And we think this has to do with the late heavy bombardment and all the asteroids which hit the moon and then presumably hit the Earth as well, and all the inner solar system, as the migration of the planets led to a scattering of a lot of asteroids.
A question from Charlie: Does JWST work 24 hours a day?
It does.
Yeah,
absolutely. If someone is able to punch in the commands, then they definitely use that time. It's as efficient as they can make it.
Yeah. Okay, maybe one more question, because we're running out of time here. This is a technical one from Ken. Why were mirrors images of a lower resolution than near cams?
Right. Longer wavelengths lead to larger pixels, which leads to lower resolution images. It's just a function of the wavelength. So as you go to shorter wavelengths, you have smaller pixels as a result, and that leads to finer focused images. I think that's what they're getting at, right? Why mirrors pixels are so big.
So this is physical pixel size because of the wavelength. The wavelength of the light is basically it's a geometric issue.
Right.
Pixel size. Yeah. Okay. Well, thank you, Richard. I think we've gone a little bit over time, but it's wonderful to speak to you. Just a question, if there's people watching thinking, "Oh, I'd love to get into astronomy," how do you get time on a telescope like this? What is the process? So when you said, "Oh, I'm going to get time on that. I'm going to get time on JWST," what do you do?
Well, it's a bit of an intense process. I'm not going to lie about it. I started about 6 months before the deadline. I started putting together the team that I wanted, and I started thinking about the actual framework for the project, and then slowly started to piece together, what do we know from the literature, where are the gaps, and then build the science from there. You really, to use a telescope like this, you've seen the images and the things that are possible with this thing. You have to pitch the highest priority science that no other facility can do. And so in my case, for solar system objects, we need to get above the atmosphere to get at, for example, CO2, because we can't do those measurements from the ground. So you really have to sell that story. So you have to have compelling science, and you also have to say why some other facility that's easier to access can't do it, because JWST time is so sought after. They only want to give time to programs that really need it.
Yeah. So if you say, I'm going to do observations of Saturn's ring, somebody's going to say, well, you can do that with a telescope on Hawaii. So don't.
It depends on what you want to do, right? I mean, if you want to get at a wavelength range that you can't do from the ground, then you've got something. You got something you can run with. But in general, you want to try and pick targets that you can't do from the ground.
Yeah. Cool. Thank you very much. We have a super sticker gift from Lulu. So thank you, Lulu. You have been watching SETI Live with Richard Cartwright. Thank you very much. We will invite you back when you have had your time on the telescope. Maybe we'll see some of your spectra, which will be fabulous to look through.
That'd be awesome. Thanks for having me, Simon.
Yeah, of course. SETI Institute is a nonprofit organization in Mountain View, California. We do rely on your donations. for events like this, to bring them free to the world. So please, do send a donation if you can. We will be back next week with another SETI Live, and this is also being recorded, so you can watch this on our YouTube channel, as with all of our other SETI Lives before. And take a look at our website as well, www.seti.org, for all the latest information and news out of the SETI Institute. Thank you, everyone, and goodbye.